do we log? But can I just plot the graph? Why do I need to go through this log thing? Especially those of you who don't do maths but do physics, you brave soul. How? Okay, let me try to sell the idea of doing log for you. Okay, so we log values for two main reasons. All right, number one, which is most of the time in your paper 5, we log numbers because we want to linearize exponential functions. So your exponential functions can take two formats. Okay, I'm going to show you one from a past year question. All right, but this is from question 1 lah. Okay, so here it says that a student uses a Hall probe to investigate the magnetic flux density due to a magnet. Okay, sure. Maybe you have tried this question already. So the one thing that I want to focus on is this equation. Okay, so it is suggested that the relationship between B and P is this one. And you are asked to prove the relationship. Okay, show that this relationship is correct. So show that the relationship is correct. You're going to test the relationship. So those of you who do maths, to test relationship between B and P. So those of you who do maths, right, you will know if I plot a graph of B against P, okay, you think about the format. The format that you are more used to is A, this whole thing in front. This whole thing in front becomes our A. Okay, cannot see that. Hang on, let me highlight for you. This whole thing in front becomes your A. Okay, and then this is E to the power of negative. This is another constant K. So this alpha here, this alpha is your K. And what are our variables? The one that we change one. If you're thinking that those variables are B and P, then you're correct, lor, because there B and P is here. So in maths, variables are X and Y. So this will be Y and this will be X. Ooh, E to the power of negative KX. Is this a straight line? Miss Noah, this graph in a straight line. In fact, this graph look like this, right? Where this is, where this is A, this is Y against X. Okay, so if the graph is not straight, how can I test the relationship? It is very hard to test a relationship of a curved graph. So in physics, we only want straight lines. Okay, so only straight lines can prove the relationship between B and P. So obviously I can't plot Y against X, neither can I plot B against P. So I also cannot plot, this is B, this is P, and this value here is K and I. I don't have straight line, and the reason why we want straight lines, if you're asking another why, this is to reduce errors and uncertainty, specifically random errors, because you will have a random distribution of points, but you can still draw your best fit line. We can also detect if there's zero error, because for example, if I'm not supposed to have a y-intercept, but I have a y-intercept, then this means that there's zero error. Maybe need to calibrate or adjust my setup a bit. So this is the why. Okay, if you're watching this video, this is a deep dive. Okay, this whole, whenever you are forced to do something, you may be asking why, or your brain may be struggling. Actually, why that? So this is why. Okay, we prefer straight lines because we can draw best fit. That help us reduce random error. Best fit line. Okay, we can also detect zero error using the y-intercept. by checking y-intercept. So this is why we linearize. But how do we linearize? Well, you look at this equation, we're going to proceed from there. Right, so here is how we linearize. You see this b, I copy first, I copy the equation first. K N I e to the power of negative alpha p. So when you linearize, right, you got two choices. Option 1, you either take log. Option 2, you take ln. Now, whether I take log or ln depends on the equation that I see. If I see exponent here, like this e, I am surely going to take ln. Because why? Remember in the beginning of the video I mentioned before, ln is log base e. If it's the same base, I can eliminate. Let me show you, okay? So let's say I ln both sides. All right, remember, good practice will be to ln whatever you see on the left and then just ln the whole thing. Put the whole thing in the bracket, the whole thing, all of it. The whole thing and the kitchen sink, put it in the bracket. So this KNIE negative alpha P, just throw only, just throw. Throw only, decide later. So this will be ln, Okay, but now it's time to take a breath and pause. And then you ask yourself, this K, this N, this I, this K, N, I, they multiply, Oh, so if they multiply, means I can use this identity ln or log AB is equal to ln A plus ln B. I can use this identity, bro. But do I really need to split everything out? Do you write it as ln K plus ln N plus ln I? No need lah. Because K times 10 times I, they are all constant. I mean, if I want to, if I need to, I can split them, but I'm just going to keep them together. So what I'll do is I will keep these three together as my so-called A. And this thing at the back, this e to the power of negative alpha p, this will be my B. This whole thing is B. Okay? Because it's multiplying. Right? So in this case, if I continue the story, I will have ln B is equal to ln bracket KNI plus ln bracket e to the power of negative alpha p. Okay, Ken. Now there's something that I can do whenever I see this ln e. Because ln e is actually log base e, number also e, 1. If the number and the base the same, you get 1. So hopefully that explains to you why whenever I see a natural log e, exponent e, I will think about using ln, the natural log, because e is 1. And I like 1, man. Let me show you why I like 1. Okay, so I like this one because you see here, this alpha p can migrate downstairs because it's a power. Okay, and then this is ln e. Bless your soul, ln e, you are 1. Oh, well, then I know what graph to plot already. Right? Here, I will get, I rearrange, negative alpha p plus ln K and I. Ooh. Now let's think about what is the general equation of the straight line. Okay, compare with the general equation of a straight line. And that equation will be y is equal to mx plus c. So this should be your y-axis. Okay, come. Let's draw and label together. Ding, 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 ding. This is ln b. Okay, we have y. What about x? Well, it's like it fits perfectly, perfect fit. This x will be your p. Okay, before I continue, we can go back to the question and double check. we want to test the relationship between B and P. So both of these should be on your axis. Doesn't have to be pure B, doesn't have to be pure P. Can be B squared, can be 1 over B, can be P power 10. But we do have BP here. So we are quite on track. Okay? So from here, I can tell that this is a straight line. Why? Because, well, alpha is constant. Alpha is constant. Also, KNI is constant. How I know? Okay, I mean, normally the question will tell you, like the question will tell you, okay? K is a constant, N is the number of turns, which is constant, okay? And I is the current in the coil, also constant. Okay, alpha constant, KNI also constant. So because of this, the graph that I expect to get is something like this. Negative gradient. And what is our y-intercept? Ln KNI. Okay, so the initial graph looks like this. No nice. But if we ln the y-axis, then we get straight line. So imagine the meme. This one, the one. No. But this one, we want. Okay, straight line. Straight line is best. You know why? Because now I can find constants. I can say that alpha is actually equal to, so I'm going to write size number 1. I can say that the relationship is valid if, hang on, before that, I need to tell, so if this is paper 5 question 1, I need to tell the people what graph you want to draw. If not, you suddenly say relationship valid if the graph, what graph? Or means I draw axis like that, can I? Don't risk it, guys. Don't risk it. Always have a formal statement. You must always formally state what you want. So you just say, plot. I'm going to plot a graph of ln B against P. All right. And the relationship is valid if the graph is a straight line through origin. Where got origin? Straight line with y-intercept. So here's how you can check for zero error. Okay, what you could do is, if you know K and you know N and you know I, you know what the actual value of y-intercept is. So if let's say your line is on top here but parallel, or your line is below here but parallel, it means that there's zero error. Okay, so I'm just gonna draw a line here. So if this is this line, this one is line with zero error. So this is what I mean by we like straight line graph, because we can tell if there's zero error. And if let's say your plot is like this all over the place, I can also balance out the best fit line. Okay, so these are all my plots. I can balance out the best fit line. So all these plots are zero errors. I'm just gonna also write that down for you. 0. Hopefully you're writing together with me as well. 0. Random errors. Average using the best fit line. Okay. Right, number 3, the reason why we linearize this, besides proving the relationship, part of the power of linearizing is that we can find constant if we need to find constants. For example, we can find alpha. So alpha here is actually equal to, or rather, I'm just going to start from the top. So if you look at this part, m, the gradient m is equal to negative alpha. So I'll write that first. I will say that gradient m is equal to negative alpha. So alpha is equal to negative gradient. Miss, can I write m? Can. If you define m like me, can. But I normally write like that for the examiner, because this is what appears in the mask. So alpha is equal to negative gradient. you must, right here in bold red letter, must write alpha as the subject. So if you leave it at this line, it's wrong. So write until here. Okay. Same thing if let's say you want to find k or n or I. Let's say you want to find k. So my y-intercept, which is c, is equal to this whole thing, ln k and I. C is equal to ln k and I. So now we want to bring the ln back to the other side, So when you throw the ln back, okay, it becomes e to the power of y-intercept. Okay, this will be equal to k and I. Okay. So think about ln and e, or specifically like that lah. Let me write down another example for you. So if you want to think about where this is coming from, let's say I have e to the power of a is equal to b lah, for example. Okay, I want to find b. So I'm going to ln both sides again. We have done this before. I will do this again. This is equal to ln b. Okay, and this is a, ln e is equal to ln b, and this whole thing become 1. So a is equal to ln b. So you will see that when this e so-called go to this side, it becomes ln. The ln come back to this side, it becomes e. All right, so whenever the ln goes over, you will get this e to the power. I mean, it depends on how much maths you do. So for those people who do maths, it's actually very second nature. You reverse back, you get e. E to the power of y-intercept is k and I. Don't leave your answer like that. Oh, I know you have finished it. We are looking for k. Again, k must be the subject, the constant that you want to find, subject of equation. Okay, so from here, k will be equal to e to the power of y-intercept, I write short form lah, divide by ni. Wow, very important. You please write this in this format, okay? All right, so if you need to brush up your maths, do so. It's pretty important here. Okay, so this is the usefulness of linearizing your graph, and because of this, the usefulness of applying ln on both sides when you get an exponential situation. Okay, I'm going to give you another example where we will use log base 10. So how do you know when to use ln? Whenever you see this e, this natural, this exponent. Okay, when do you use base 10? Let me show you. Okay, so we've done this example, okay, where we use ln. Now I'm going to give you another example where we will use log, which is this equation, all right, which is also the question paper that we will discuss at the end of this video or this video series. Depends on whether we plan to chop it up or not, I don't know. So example 2, when do we use log? Okay, we use log when the question tells us to, or when the format looks like this. Like this, right? You can use log or ln. So whenever there's no natural log, you can use log or you can use log. All right, I'm going to fast forward and show you the question now. All right, this is the question that that was set, and you will notice that they actually tell you that a graph is plotted with log nu, this pronunciation of the pronunciation for viscosity symbol is nu. Okay, like that feeling where you made a conversion error. Nu. So this log nu on the y-axis and log theta on the x-axis. Okay, so if they already mentioned to use log, then you have to log. If not, you could ln. So I'm going to do both for you so that you understand that actually it's just preference and also what is available. Most computers can log better than they ln. it runs faster. That's why log 10 is also somewhere inside our option. So I copy the equation first, p theta power q, and then I add log to both sides. Log base 10 nu is log base 10 p theta q. Okay, so when I add the log base 10 inside, it's important to see which one are the multiples that you can split. Okay, I can see that p, this is p times theta power q. So what I could do here is I could continue this with log nu. This is equal to log p plus log theta power q. Okay, so then if I rearrange, this is log nu. I can bring the q down. So this is q log theta plus log p. Okay, so I rearrange, I bring this one here, and then I shift the index down. So if I compare with the general equation, y is equal to mx plus c. Now I am plotting a graph of, okay, think about your axis. I will draw here for you. Y-axis is log nu. Okay, x-axis is your log theta. This is y, this is x. Right, gradient, if q is positive, then gradient is positive with y-intercept. Let's assume it's positive first because we don't know. We don't know whether q is positive or negative. Don't know. So I'm just going to put if q is positive. Don't know. And p is positive. Also don't know. All right. But in this case, you should get something that is a straight line with y-intercept. Straight line with y-intercept. So it doesn't pass through the origin. Okay. And then in this case, your gradient m is equal to q. And also at the same time, your y-intercept c is equal to log p. This is neater, okay? But if let's say you decide to ln, if you decide to ln, I'm going to change it to a different color pen, but I'll copy the equation first, okay? So if I ln both sides, I'm going to ln here, ln nu, okay? And then this p theta q, I will ln again, ln p theta q. So I think you will arrive at the same equation, right? This part here, you're going to write ln nu. Everything else is the same. So I can just write this one as q ln theta plus ln p. So we will still get a similar graph. I'm going to just draw this here for you to see. This will be ln nu, and this will be ln theta. Then of course, the absolute value is different. So q is still gradient. We will still get straight line with y-intercept. So whatever that is here, I'm going to copy and paste. It will be here as well. But the only difference now is not the gradient. Gradient is still equal to q. There. But your y-intercept is now ln p. Y-intercept is ln p. Hey, miss, look the same. No. So now if you want to find p, you will take 10 to the power of y-intercept. If let's say you want to find p, if you plot the second graph, you will take e to the power of y-intercept. Okay, so they are very similar thing. They are interchangeable, but they are not identical. Left and right also not the same. Also not. They are not identical. So you will get the same shape, just like I've shown you in the early part of the video series, okay? But the important thing here is to know what graph you're plotting. Follow the question. But if it's in this format, log or ln also okay. If it's in this format, there's an E here, then don't use log, not recommended. Only use ln, because we can monopolize on the fact that ln E is 1, but log E is not 1. All right, so that's how and that's why we log for linearization. Okay, so next part, I'm going to talk about the second purpose of log, which is sometimes we need to deal with big numbers. Okay, so the first purpose was for linearization, and the second purpose of doing log, why log, is to handle large or small numbers. Specifically numbers with a lot of zeros. So it's either like 74,000 or 0.000023. Okay, let me give you an example. Okay, so let's say you are dealing with numbers like this. So this is the given equation. T squared is equal to KR power 3. Okay, and this is also a past year question. No? So you can log both sides. All right, so I'm going to just do this as practice with you, or you can pause the video and do it. Okay, so if I log both sides, this will be 2 log. Okay, let me slow down for the people who needs it. So log both sides first, KR power 3. Okay, once you log both sides, then you ask yourself, are there identities that I can use? Yes, my friend, you can have 2 log T is equal to log K plus log R power 3. This power 3 I can throw down now because it's index, okay? So this is 3. And then I rearrange log. I want log T as the subject of my equation because you see here there's a log T here, okay? So my graph would be looking like this. So all these sketches is something that you do on the side to help your brain. It's not part of your working. So this is log T. I bring this one over, so I will get 3 over 2 log R, the half I bring over. So here is my log R, then log R, okay, plus log K over 2, or 1 over 2 log K. So in this case, you actually will get a graph like that, where the gradient, because you are plotting the graph of y is equal to mx plus c. So the x-axis is r, log r, and the y-axis is log t. Okay, so your gradient here will be 1.5. And your y-intercept here is half log k. All right, so this is example of linearizing again. But let me show you something. Let's say, for example, you don't log the graph and you want to find, let's say, t squared, which is still okay, 10 to the power of 3. So if I look at this equation, let me copy this down. Okay. Ta-da! So you see, if I want to deal with t squared, let's say I'm dealing with big numbers, it's t squared. I'm going to take 24, you see a prefix here, times 10 to the power of 3 square. And then this one is k. And then this 129 times 10 to the power of 6 cube. Wow, so difficult, much difficult. You know why it's difficult? Because your computer or your calculator now need to compute very big numbers. There's 10 to the power of 6 here because of the square. There's 10 to the power of 18 here because of the 6. Of course, now we tend to take things for granted because we are humans with modern computing power. So all this calculation, your computer is like easy cakes. But let's say you need to run thousands of calculation of repeated experiment. So not just 6 reading and you draw a nice paper-fied graph. Let's say you are a postgraduate student or you're doing your final year project in uni and you need to use a lot of data, like gigabytes upon gigabytes of data. Look, your computer will hang. So to help your computer from not hanging, I would prefer to, let's say, use this equation instead. The one that I derived just now. Log t is equal to 3 over 2 log r plus 1 over 2 log k. So let's say both purpose is to find the value of k. So in this case, my k, I will have to take 129 times 10 to the power of 6 power 3 divide by 24 times, no, it's reverse. Give me a sec to change this. K would be 24 times 10 to the power of 3 square. This is very taxing for the computer to run because the numbers are very big. Okay, whereas this one, let's try. We're going to log t now. Okay, so I will take log, C is t, 24 times 10 to the power of 3. Okay, is equal to 3 over 2 log r. So log, what is my r? 129 times 10 to the power of 6. We'll press calculator for both. Okay, I mean, nowadays this may be okay because your calculator is a powerful one, but last time maybe not. Okay, so let me press the one on this side first. Okay, I'm going to take 24. Hold on, I'm going to take 24, 10 to the power of 3 square, divide by 129 times 10 to the power of 6 power 3. So if you look at this number, it's very small, and your calculator, there's no struggle here because I have a powerful computer, you have a powerful computer. This thing is pretty good already. But if let's say you're running a lot of data, this may be a problem. So these numbers are very big and very small. 2.68 times 10 to the power of negative 16. 2.68 times 10 to the power of negative 16. Okay, so I'm going to write here. It is okay, but if many data set, then computer CPU GG, gone case. Bye-bye. Okay, what about this one? Let's see. Ta-da! Okay, I'm going to log this one first. Log 24 power 3. It's 4.38. I think my calculator or my computer is more happy when dealing with 4.38. Okay, what about the other term? Let's see. Oh, my calculator died. Okay, the other term will be 3 over 2 or 1.5 log 129 times 10 to the power of 6. This one is 12.16. So I'll write 12.165 or 12.17. 12.17 plus half log k. So you can see from the calculator perspective, it's much easier to take 4.38 minus 12.17, okay, multiply by 2. This is my log k, negative 15.58. Negative 15.58. So when your calculator is doing the computing, after we log, the numbers are smaller. Circle. All these are small numbers. This one on. It's easier to handle. No need to power, easier on the computer. No need to 10 to the power of something. Easier on your brain also, right? If let's say you don't have a calculator, but you have the log table, okay, you can change out these smaller numbers. It's easier to use. It's not obvious now because you have a powerful calculator and you have a powerful computer. But it was very important to them back in the 50s or 60s when they didn't have a proper or a powerful computer. And it is useful for you to learn how to code an equation that's easier to run. Of course, you may be saying that, don't I need computing power to change log 24 times 10 to the power of 3 to 4.38? You do, but the computer is pretty good at doing this because it is a matter of looking up a value from a graph. Remember that log graph that I've drawn just now? You just need to have that graph inside your code. Your computer can retrieve that data. Retrieval is easier than processing for your computer. Okay, anyway, I'm going to continue here to find my k. So k would be 10 to the power of negative 15.58, which this is the only difficult part for your computer to do lah. So I'm going to put 10 to the power of negative 15.58. I want to paste the answer in, but never mind. So I'll get 2.63 times 10 to the power of negative 16. Of course, the answers are not going to be identical. Okay, so the compromise that we are making here is a less accuracy depending on the rounding, depending on SF lah, basically. Okay, so whatever I have on the left, this is the accurate one because I key in pure. I didn't convert here, convert there. This one here, I convert already. I round numbers. I convert this log 24 times 10 to the power of 3. I round the number. I convert this 129 times 10 to the power of 6. I round the number. Okay, so this one is less accuracy and it's also depending on how many SF, whereas this one is a direct calculation. Okay, so let's go back to the table and I want to talk to you about SF because remember I said this accuracy depending on SF. So now the question is, how many SF should I put in if let's say I'm filling up the table like this? Okay, so when it comes to SF, what is important to know here is that our SF will follow the previous data last time lah. But there is a special case for log or ln. Okay, there's a special case for log or ln when it comes to SF and DP. So normally you will see this thing here, this 129 is 3 SF. So when you go to log calculation, it should be 3 or 4 SF. That is normal. That is other values. That is anything besides log. But currently we are doing log. So this is not 3 to 4 SF. This should actually be, when you have 3 SF, you transfer over here. It should be 3 or 4 DP. This part here, very important. SF to DP. Miss, why so weird one? Because currently we are dealing with log. Okay, so here I purposely didn't follow. I take the SF or the SF I plus 1. So you can see this number is not very accurate. It's not really the actual number because I actually should follow the decimal point. The first number here, the reason why we follow the decimal point, if you care to know, is because this number only gives me information about prefix. Like for example, 24 times 10 to the power of 3 is actually 10 to the power of 4. Right? 2.4 times 10 to the power of 4. So this information is not that significant. It's not as significant as the numbers at the back that will tell me, is it 1 times 10 to the power of 4 or 9.9 times 10 to the power of 4? Don't know. So it depends on this 3, 8 lah. Okay. So we will take 3 to 4 DP because the DP tells us what the number is, whereas the first digit tells us what is the power or what is the prefix. 10 to the power of 4 in this case. All right. So here, this means this 24, sorry, this 129, I will press log R again. I just want to press my calculator lah, 129. times 10 to the power of 6. Hang on. This will be 8.1105. So I can write 8.111, or I can write 8.1106. Press for you lah. Sorry, let me press here for you. Log 129 e to the power of 6. 129. 129? What did I type? 126. 129 e to the power of 6. So 8.110589. So you either write this as 8.111 or 8.1106. Okay, up to you lah. I prefer less lah. Less is easier to plot. Okay, so what about this one? This is 2SF. So when you transfer over here, it should be 2 or 3 decimal point. Oh, okay. So can I take 4.38? Sure. 4.38 is fine. If you're wondering why this is not 8.11, this 12.17, it's because the 3 over 2. I already multiplied 3 over 2. Okay, so this one you can write 4.38. You are good. So if let's say I increase the SF for this one, I put 8.111. Okay, let me change this one. So I write an alternate line here. If I take the correct SF, it should be 4.38 is equal to 3 over 2, 8.111, 1 plus half log K. All right. So this one, I'm going to quickly press in my calculator. This will be negative 15.573. Okay, so 10 to the power of the answer. This K will be 2.673 or 2.67 times 10 to the power of negative 16. 2.67 is closer to 2.68. So this is where log, this is why for log it matters that we take, instead of the DP, sorry, instead of the SF, we take the DP. Okay, so as a recap, whenever you have data, right, you will have two things. You will have raw value, and then you will have some calculated value. Let me move here a bit. Okay, so if your raw value is, let's say, 3 SF, when you move to the calculated value, it should be 3 or 4 SF. So basically, we are following least SF or +1. This is for all operations. Except what? Except the whole video today law, except log or ln. Okay. The exception for log and ln is if you have 3 SF, when you move here, it would be 3 or 4 DP. So least SF become DP or +1. This one is for log or ln. So whatever you learned previously in paper 3, paper 5, it still applies unless you log and ln for accuracy purposes. Okay, I took the pains to show you the calculation that nobody showed me because my teacher just said, you press your calculator and figure it out. So it took me all of 2 hours or 3 hours of my life. Okay, so hopefully that saved you some time. Okay, so this is why whenever we have log and ln, we transfer from SF to DP. Because if I stick to the SF convention, let's say for example, this is 3SF, I stick to 4SF, this 24 is 2SF, and then I reach here, I take 3SF, then my answer not that accurate. But if I follow the decimal point convention, my answer is a little bit more accurate, not the best. Okay, so this is what I mean by ease of handling large numbers. So the first purpose of log, linearize. Second purpose, so that the numbers are small. Small numbers easier on computer. Okay, so those are the purposes of log and ln. And the important skill that you also have to remember is that the weaknesses of using log and ln and small numbers is that you do a lot of rounding, and in that rounding you lose accuracy. To try to help maintain that accuracy, we cannot count the numbers before the decimal point, because the numbers before the decimal point represents the prefix. So that's why we only take the decimal point. If it's 3SF, you do 3 to 4 dp. But for everything else, power 2, square root, all that, you can still stick to what we know so far, which is follow the least SF. Okay, cool. So this is this part of the log and ln series, right? Why we log? We don't want our computer to GG when dealing with big numbers. All right, and how to handle the limitation. Okay, that's it for this particular video.